Throughout the history of life on Earth, there has always been extinction. In fact, extinction is a healthy and natural part of life. If we were to count every single species that has ever lived, we'd find that more than 99% of all species that have ever lived have gone extinct. However, as we start looking at extinction at different levels and different rates, there can be some issues that are raised that can cause a big problem for ecosystems and even the worldwide health of the global ecosystem. Now, to do this, we need to begin to examine and start to think about what causes a species to go extinct. Okay, so what causes an extinction? Now, it turns out that if we want to be very general, that this is a very easy question to answer. Extinction is caused by a failure to adapt to a changing environment. Now, there are some things that can make that more difficult. So, for instance, if we have a species with a very narrow range of habitats or a narrow range of behaviors, it's more likely to go extinct because it's not going to tolerate change. Also, if we have change that happens very, very rapidly or happens on a very large scale, that's going to cause more extinctions. And so although the specific exact cause of an extinction might vary, it might be an introduced predator, it might be a volcanic eruption, it might be a change in the pH of the oceans, and the list goes on and on. In general, we can say a species was unable to adapt as the environment changed. And if we look historically, we can see all sorts of interesting patterns. And so in some of the coming lectures, we're going to be looking at some of these. One interesting pattern that we see over the last 50 to 60,000 years is an extinction of megafauna. That is, large animals that have played very important roles in the ecosystem, but now, in a relatively short, recent time have gone extinct. So this includes mastodons and woolly mammoths. This includes giant kangaroos and predators and giant herbivores about the size of cows that were all marsupials in Australia. This includes many saber-toothed cats that were once dominant predators in North America. And it includes the giant sloth, which was an incredible, important part of the ecosystem in South America. Now, there are lots and lots of others, and so we're going to look at these trends. And part of the trick of studying the fossil record is trying to understand why we see changes in the fossil record. So let's take a look at this. In the old world, the answer may be different than what's going on in the new world. And so people began to study this, and they noticed two major changes that seem to be candidates for why all these big mammals were going extinct. The first one was humans, and as humans began to become more and more widespread and more numerous, they began to have much more of an impact on the globe around them. Not only that, but humans migrated to new areas and were introduced to areas where they had not lived before, and so that's a change, in fact sometimes a very massive change to that environment. The other cause that was a potential candidate for the extinction of these large mammals is global climate change. Now, this was not human-induced. Humans have only been having an impact on the global climate for the last 100 years or so. But the globe has been generally warming. So we've gone through a series of ice ages over the last 100,000 years or so, and there have been warming and cooling trends. And over the last 50,000 years, there's been a general warming trend, and glaciers have retreated, and the globe as a whole has gotten much warmer. So if we look and if we try to match these extinction events to when humans arrive and the climate change, we see some interesting things. That human arrival seems to coincide with the vast majority of extinctions of large mammals in the northern United States, Canada, and Mexico, so in North America. So humans seem to be the major cause there. There's not a lot of data both from the archaeological side of humans and even the paleontological side for bones. So we don't know for sure in South America whether it was humans or not. In Australia, it was almost certainly humans. Humans seem to be the major one. There's some really interesting and exciting groups of organisms that are now gone, or they just have a remnant left. Now, in the old world, it's a little bit different. In Africa, we're not sure, but I remember in Africa, we have a long history of hominids, that's our close relatives, and eventually humans living side by side with large game. And Africa had many fewer extinctions of their large game. And in fact, Africa has the most intact megafauna of any of the continents. They still have elephants and wildebeest and zebras and all these large predators. And so humans evolved to evolve there together. And then finally in Europe, where also we have, going back 50, 60,000 years, modern humans, and even more anciently than that, we have Neanderthals and other hominids living there. It seems to be that climate is the major thing, and so humans evolved as part of this ecosystem. So, for these, we're looking at proximate causes. So was the proximate cause climate change, or was the proximate cause humans? Now, the ultimate cause is still the same. We mentioned that in the slide before, right? The ultimate cause is failure for these megafauna to adapt to a changing environment. And we often think of humans as kind of this artificial thing, but really we are part of nature. We're, for better or worse, part of this globe, and we are changing the ecosystem to massive amounts. Now, today, obviously, humans are having a global impact, and it's speeding up. In fact, we're going to look at historical records of mass extinctions or cataclysmic extinctions in 3.6c. And then we will start talking about the impact that humans are having on the globe today. But let's put a pin in that and we'll come back to it. We can think of an environment almost like a plate that we try to stack grapes on. This is my analogy. I've never done this experiment in class because it's rather cruel. Not really an experiment, but more of a demonstration. So imagine I gave you a small plate, maybe a petri dish, and an unlimited supply of grapes, and said, without using any glue or any sticks or anything, stack as many of those grapes on the plate as you can. Now what you would get to is a point where you have saturation. You have as many grapes as possible that are on that petri dish. Now, if you worked a little bit hard, you might get one or two, but eventually you're going to have a little landslide and several will fall off. Well, these grapes in this analogy are like species, and the dish or the plate is the environment in which they have to survive. And so, of course, there are different niches and different needs for different species in these environments. Some need a lot of space and a lot of resources. Others may be able to get by with just a very small amount of space. And so the grapes are really not the best example. It might be better to look at really large fruit, really small fruit, and everything in between and see how many you could stack on a plate. And then when a grape falls off, that would be like an extinction event. And so when a population goes extinct, it means that that usually allows a little bit of extra room on the plate, in our analogy, but in the ecosystem. And so extinctions allow for new species then to move in and start to adapt and fill up that niche that was vacated by that extinct species. Now this process we'll just call background extinction. And this is a natural, normal, healthy part of ecosystems. In fact, this is how ecosystems stay new and vibrant, is by continually kind of changing. As things are unable to adapt, they open up space, new species come in, and populations and ecosystem as a whole evolve and change as the world changes. Now imagine, and this is the cruel part of this experiment, imagine I came up while you were trying to stack these grapes on a plate, taking it as a challenge, and I just shook the plate like crazy and most of the grapes fell off, leaving only just a few behind. That is a cataclysmic extinction event, right? And when a massive environmental change occurs, most species are not going to be able to adapt, especially if it's a very rapid environmental change. And so we'll have a huge percentage of all of the species found in an environment going extinct. That's called a mass extinction event or a cataclysm. Okay? So think of that analogy, and we're going to talk about these and look in the fossil record of evidence that we can see for cataclysmic extinction. So random extinction is not really dangerous. This is pictured in A here. You know, a few species here and there. Eventually new ones will come in, and as long as the rate of extinction is not accelerated, it won't matter, and we'll end up with still about the same number of species. Even though they may change, we won't have any fewer or any more species as time progresses. We'll just have new ones that evolve and new ones that come in and take the place of former species that have gone extinct. Now, even if we don't have a cataclysmic extinction, there's still some ones that worry us, like in B and C. So if we have a focused extinction event where all of one group of species are going extinct. So we're going to look at an example here in a little bit of amphibians. If we see all frogs going extinct, then even if we have the same number over time down here as we have here, it's more worrying because we have an entire group that is now missing from the record. So focused extinctions are a little bit more serious and cause conservationists and people that are worried about biodiversity to take notice and to try and prevent those sorts of things. So here, same thing, you know, they're all one group. They're all kind of at these basal nodes, or these nodes that are close together. So focused extinctions are a little bit more troubling than kind of random, healthy extinction for an ecosystem. Now, to close off this discussion, I just want to do a quick review. We talked about this at the very beginning when we looked at the history of life on Earth, and we're going to revisit it a little bit here today. So it's worth reviewing. Remember, a fossil is a mineralized, preserved remnant of a once living organism. And in the vast majority of fossils, though they may maintain a huge amount of detail, especially of hard structures and sometimes soft tissue, they don't have any of the original organic material. So there's no DNA, there's no fats or lipids, there's no carbohydrates, a nucleic acid, all of it's gone. Okay? And what's left is a mineral version, crystallized version, that preserves what they look like without any of the original material. Now, we cannot directly date fossils, remember that, so review that. So I can't take a sample and do some sort of analysis of the mineralized bone and tell you when that organism died. However, what we can do is relatively date this igneous layers of rock and then use those, take that back. We directly date the igneous layers of rock. And then we use position and some basic logic to help us get a relative date for fossils. And so what this means is that fossil dates are very, very accurate. However, they are not very precise. Okay, so I'm going to actually add that here. Let's put that one in. So I thought I had it there, but and then let's talk about the difference between precision and accuracy. Now, ideally, when we're gathering data, we have both precision and accuracy, but we can't always have the best of both worlds. Okay? So think of it this way. Precision is how certain are you about the range of dates. So if I say this organism died 10,555,364 years ago, that's a very precise date. Okay? Now, it may not be accurate, though. So if I say instead this organism died 3 to 3.2 million years ago, that may not be very precise. It's a wide range. However, it is a better estimate of accuracy. And so those ranges that you see on fossil dates are based on our uncertainty about the data that we've gathered. And there are various factors that can contribute to that uncertainty. And so we'll see ranges there. And so what this means that if we're careful and we do it right, although we may not have great precision, we have good accuracy. And if you've got to give up one, accuracy is the one that you want to keep, and you'd rather give up a little bit of precision, right? So it takes a little bit more work, a little bit more effort, but you still have a precise date. An accurate date. So let me just give you one other real-world example just to illustrate this. If you go to a carnival, you'll often see a booth, right, or a man standing there, and he says, guess your age or guess your weight. And when you look at the rules, there is a margin of error, right? So if he had to guess your age to the exact day, you'd always win the prize, right? So they have that margin of error that allows them. So it'll be like plus or minus 2 or 3 years, right? But again, that's part of the rules of the game. If he went up there and said, guess my age, and he thought and said, okay, you're somewhere between the ages of 2 and 102, right? That's a very accurate guess, but not very precise. And so ideally, we'd be able to do both. But with fossils, and we're not as bad as 2 to 102, but we might see something that says this fossil is 3 million years, give or take, 20,000 or 50,000 years. And so those give us a good idea of how well we are doing at estimating those dates.